Good evening, everyone, and thank you for joining us today. I'm Gagan Martin Potra, Senior Engineer in Engineering and Innovation Unit, here with my colleague Ben Rosser, Corn Specialist from Agriculture Development Branch, and Julie Purenga Minsinga, Economic Business Advisor, Economic Development Branch, OMAFA. We truly appreciate you taking out time from your busy schedules to attend and participate in webinar on efficient green drying techniques for quality and profitability. Tonight, we are fortunate to have two distinguished researchers from Lethbridge sharing their expertise on green drying. Dr. Digvir Jayas, President and Vice Chancellor of the University of Lethbridge, will deliver a talk on ambient air drying of cereals and oilseeds. Following that, Dr. Chandrapan Singh, Radar Research Chair in Agricultural Engineering and Technology and Director of Advanced Post-Harvest Technology Center, Lethbridge, will present on high temperature green drying, do's and don'ts. To begin with, I would like to invite Ben Rosser to present the land acknowledgement, followed by Julie Mansinga sharing the housekeeping details. Thank you.
We will begin the event, Efficient Grain Drying Techniques for Quality and Profitability, by acknowledging that we are meeting on Aboriginal land that has been inhabited by Indigenous peoples from the beginning. As settlers, we're grateful for the opportunity to meet here, and we thank all generations of people who have taken care of this land for thousands of years. Long before today, as we gather here, there have been Aboriginal peoples who have been the stewards of this place. Ontario is covered by 46 treaties and other agreements. In particular, in Guelph, we acknowledge the traditional territory of the Attawandaran. This territory is covered by Upper Canada treaties. We recognize and deeply appreciate their historic connection to this place.
Hi, my name is Julie Puari Mensinga, and I will be moderating the chat for this session. For those who don't know me, I am an economic and business advisor with the Ministry of Agriculture, Food and Agribusiness in Northern Ontario. A few housekeeping items before we begin. We are in a Zoom webinar tonight, which means you do not have the ability to unmute your microphone or turn on your camera. If you have questions for the presenter, I would ask that you enter them in the chat box. I encourage you to write your questions as you think of them so you don't forget them. And we will have a question and answer period after each presenter. So with this, let's begin. I have the pleasure of introducing you to tonight's first speaker, Dr. Digvir Jayas from the University of Lethbridge. Dr. Jayas is a highly decorated researcher and trusted collaborator with the farming community who specializes in grain storage system and energy efficient drying systems. In 2025, he was awarded the King Charles III Coronation Medal for his work in grain storage. He will be presenting on ambient air drying of cereals and oilseeds. Please note that the webinar is being recorded with the intention to post the video on Crop News. Unfortunately, due to technical issues, the recording was delayed a little bit, and we are missing the first couple of slides from Dr. Jayas' presentation.
The properties of the grain itself. And then the biological factors are microorganisms, insects, mites, rodents, birds, and grain itself is a biological material. Again, another comment here, if the structure is designed properly, then rodent and birds should not be playing a role. And certainly in Canadian system, typically they don't play a role. But in poorly designed systems, they do come into play. And then the geographical location where the bin is situated, and what kind of a structure it is. Is it a concrete structure? Is it a welded steel versus corrugated steel structure or wooden structure? So that also plays a role. But out of all these factors, the two main factors are the temperature and moisture content of the grain. And what our goal is to manipulate manipulate these two main factors by designing system in a way that it basically gives us the long, safe storage life. So in this example is a generalized curve, which is for any grain, whether it's wheat, barley, corn, rice, lentils, or chickpeas, or all of the seed types would have a similar graph. So what basically you have on the horizontal axis is temperature is increasing from left to right, and the moisture content is increasing from bottom to top. And what you have are the zones where you have a safe storage zone. So as long as you brought the temperature and moisture content of the grain in that region, then grain is safe to store. And when I say safe to store, you can easily store for a year or more. Low risk of spoilage, where if you fall in that area, there's a potential of some spoilage. Then medium risk of spoilage, or high risk of spoilage if you have a temperature too high, or moisture content too high, or both being too high. So that gives you basically then as the risk of spoilage increases, then you have fewer days of safe storage. So this is an example of the guidelines for the wheat. The previous graph was a generalized graph for all grains. So this is an example of the wheat. So like if you were storing wheat, and if the temperature was 25 degrees centigrade, they would expect, or there's an expectation to store for more than no spoilage for at least 6 months. You need to bring the moisture down to around 11% as an example. So on the other hand, if the moisture content was high, let's say 18, and temperature was 15 degrees centigrade, even there's a risk of spoilage is there, and the grain would spoil under those conditions. So similarly, there are graphs available for canola, and our team has developed these safe storage graphs for probably, if I had to guess, probably more than 15, 20, between 15 to 20 different seed types. And these are available on the website of the Canadian Grain Commission. Other thing I want to also highlight for you is the concept, which is and that's how the near ambient air drying works. Because when you force the air through the grain for long enough time, it comes into equilibrium with the temperature and the humidity of the air. So depending on the temperature and the humidity, it comes to a certain moisture content, and that's referred to as the equilibrium moisture content. So the curve on the left-hand side you see is the single line, which is showing the equilibrium moisture content on vertical axis and equilibrium relative humidity on the horizontal axis. And that's the sigmoid shape, is typically the shape of the curve. And the curve on the right-hand side is showing you the effect of the temperature. So if the temperature was higher, then as you could see that at the same relative humidity, you would have a lower moisture content. And then at the low temperature, you would have a higher moisture content if the relative humidity was the same. So you need to understand the effect of the temperature and on the equilibrium moisture content, because that's what drives the drying phenomena. Another thing you need to understand is the process that how that grain comes into equilibrium with the air. Is it coming into equilibrium by losing moisture? So that's the desorption. Or is it coming into equilibrium by absorbing moisture? So like, for example, if you have dry grain and expose it to high humidity, in that case, it would be absorbing the moisture and coming to equilibrium by sorption. On the other hand, if you had wet grain and you were then drying that grain, then it is by desorption. So as you can see, there's a difference in the equilibrium moisture content, and that also plays the role in, especially if you have a automated control system, whether you are doing the equilibrium is reaching by sorption or desorption. And as you can see here, if by sorption, if you had the same relative humidity and then you draw a line vertically, desorption would give you a higher moisture content than the sorption would give you. This is another way of looking at the constant RH. At constant RH, moisture content decreases as temperature increases, and that you saw from the previous slide. These data were basically plotted using the EMC-ERS data based on Henderson equation and constant from American Society of Agriculture and Biological Standards. Those standards are commonly used by engineers when they are designing the storage system and drying systems. So if you want to learn more about the standards, I would encourage you to access those through the ASABE standards. This is another way of looking at the data, similar data, but here they are, rather than plotting them, they are tabulated. So as you can see here, if you were at the constant relative humidity, let's say, for example, let's say 60% relative humidity at 20 degrees centigrade, the moisture content is 13.7. But as the temperature increases, the equilibrium moisture content goes down. The numbers in red basically implies that that's where the potential spoilage can occur if your grain is in that region. And then in the black, they're implying that that's where you would have a safe storage. And would, depending on the lower the moisture and lower the temperature, longer you would have the storage time. Now, this table is for wheat. Similarly, you have this is the table for canola. Similar table as the previous table. The one thing you would notice is that the canola, if you had the same relative humidity and the same temperature, your equilibrium moisture content would be lower. So what that means is that if you want to store canola for a long period, then you would have to bring the moisture content of canola down compared to wheat. So for example, wheat, the typical storage moisture content is in the market or for trading, 14.5 is used as a dry, but that 14.5 really is not safe moisture for storage. And canola, for example, 10% is used as a classified as a dry. But again, for storage, long-term storage, particularly 10% is too high a moisture and canola could spoil. So based on a lot of data, this is what I would say, the table which sort of summarizes the recommended safe storage moisture contents for long term, like up to 1 year, versus short term, like 30 to 60 days. And then depending on what the temperature you are expecting, cool or warm temperature. So like as an example, canola, if you want to store for long term, the moisture content should be around 8%. And these are moisture content on a wet basis. Whereas the dry for trading is 10% as an example. Wheat, same thing, like trading is typically 14.5, but for long-term storage, the moisture should be reduced to about 12%. One other comment I want to make is on the high oil content canola. Like if the oil content of the canola is more than 45%, then these moisture content values should be reduced by another percentage. So if it was a high oil content canola, then 8 would go down to 7%. So with that background, I want to then talk about the forced ventilation terminology. So you would have heard terms like aeration, chilled aeration, natural air drying. So these are the different terms. So I just want to clarify. So aeration is basically is a cooling mechanism, which means that you are forcing a small quantities of air through the grain to cool the grain. It does very little drying. That means is that you might remove maybe 0.5 to 1.5 percentage point from the grain due to aeration. Typically, it's in the lower end, like more around 0.5 to 0.75 percentage point. Chilled aeration is not used as much in Canada, but it certainly can be used under the situation for the integrated pest management, where if you bring the temperature of the grain below 10 degrees centigrade, then insect activity ceases to exist, and that then can be used for controlling the insect population, for example, especially in the hot summer months. Natural air drying is the term which is commonly refers to forcing the natural air through the grain or ambient air through the grain. And in that case, the drying is then accomplished by that ambient air. The near ambient air drying is the term used when you are pulling the air over for example, over the fan or over the motor of the fan, and it's because of the frictional energy, there is 1 or 2 degrees centigrade added to the ambient air. So that's why it's referred to near ambient air drying. Basically, that extra 2 degrees centigrade. Low temperature air drying is when the air temperature is increased by, say, between 5 to 10 degrees centigrade. And then that is naturally would require supplemental heat, which could come from solar system, could be propane, could be electricity, could be natural gas. So whichever external source you use to increase the low temperature. And all of these terms, the aeration, the drying, these ambient air or low temperature drying, typically requires a small amount of airflow per unit mass of grain compared to the next term, which is high temperature air drying, which Dr. Singh would talk about after I'm done the presentation. In a high temperature air drying, depending on the type of dryer and which Dr. Singh would cover, your air temperatures could be anywhere from say 70 to 250 degrees centigrade. And then dry aeration or combination drying is that you dry the grain using high temperature drying, especially if it is a high initial moisture content, and then dry it 2 or 3 point above where you want to store the grain, and then use the ambient air drying or natural air drying to bring that temperature to the storage moisture content. So typical ambient air drying system or natural air drying system basically this is the typical system. This is from one of the papers Dr. Singh and I co-wrote on studying the flat bottom bin system. So what you see is the bottom of the bin is the perforated floor. There's a fan which is supplying the fan which is connected to the side of the bin, supplying the air under the plenum through the perforated floor. That air then rises through the grain and creating a drying front, which moves from bottom to the top. And in the example shown here, portion of the grain is dried. Then middle is the drying front, and on the top still is the wet grain. And you want to make sure enough air goes through it at the right conditions, so the drying front goes through the top of the grain. And when it has done that, then your drying is complete. And then a lot of these bins then are equipped with many sensors. So there could be a temperature cable. Some bins might have a temperature and moisture cable. Some bins have a weather station attached to it. Pressure sensors to measure the static pressure, and I will talk about the static pressure in a minute. You can have an insector which detects the insect activity inside the bin. And head space might have a temperature RS sensor, but also nowadays carbon dioxide sensors are being used in the head space or the exhaust vent where the air is discharging. Because the carbon dioxide is a good indicator of the incipient spoilage, so that's why they are used. So this shows you another way of showing the ambient air drying. So you start with the wet grain, and then you complete the drying as you move forward, move upward, and the drying is completed. Now, when you are designing the ambient air or a natural air drying system, the one thing which you have to make sure is that your fan is capable of withstanding the pressure drop which is created by the grain. And that pressure drop can be affected by the grain type, moisture content, bulk density, porosity which is also related to the grain type, foreign material, the type and distribution of the foreign material, how you fill the bin, so whether it's a spreader or a spout fill, bed depth, duct configuration, size and amount of perforations in the floor, and airflow rate and direction of airflow. So quickly, like this is an example of showing the different grain types have a different static pressure. So if you had a constant airflow rate at the same airflow rate, canola would give you much higher pressure drop per unit meter of the grain depth than the wheat would give. Or as you can see in here, wheat resistance or pressure drop is even higher than barley, for example. American Society of Agriculture and Biological Engineers again has a standard on the pressure drop, and this particular slide shows you the relationship between the airflow and pressure drop from many different grain types. And again, and the red lines are basically showing you is the pressure drop for canola and wheat, and showing you numerically that canola gives almost double the pressure drop for per unit meter of the grain depth. Now, keeping in mind, these numbers are for loose fill. So if you are a high moisture grain, then you can use the values read from this graph about 80%. And if it is a compacted grain spread or filled, then the static pressure drop number should be multiplied by 1.5 times. Want you to be aware of that. Other thing to keep in mind is the bed depth, and as you would expect, as the bed depth increases, the static pressure increases. So horizontal bed depth is increasing, and on the vertical axis, you can see the pressure drop per unit length of grain is increasing. And it's also connected to flow rate. And this is showing the effect of the moisture content, and higher the moisture content, lower would be the pressure drop for any grain type. Other thing is the distribution of the foreign material. So whether you have a foreign material in this case is referring to the chaff, is basically referring to particles larger than grain kernel, and fines is referring to the particles smaller than the grain kernels. And as you would expect, if you like 100% fines is the maximum pressure drop for the same airflow rate. And then mixture of those two. So chaff would usually decrease the pressure drop, fines would increase the pressure drop. So that should be taken into consideration when you're selecting your proper fan size. And this is an example of the spout and sprinkler fill. And then also the direction of the airflow has an effect, and I will come to the direction in a minute. So this is the resistance to airflow. Typically, the bins are filled from the top, and the air is typically forced from the bottom. Almost about 35 years ago, our team was the first one to show that the resistance to airflow is less in the horizontal direction. And when I say less, roughly about half in the horizontal direction compared to the forcing the air in the vertical direction. So at that time, I started conceptualizing and promoting in the farming community that we need to move to a horizontal airflow drying system by means that force the air horizontally, and that gives you more uniform drying, takes less energy, static pressure is predictable all the time. We did some of the CT scan and computed tomography images to understand why that difference is there. And this just is an example of that. And another example. Then we designed a full-scale drying system for a full-scale size bin, where the duct was in the center as a perforated tube, and the air was then allowed to flow horizontally and was collected on the side in the perforated tubes and then discharged to the outside. Lot of things you see in here would not be needed in a typical bin, because this is an experimental bin. So we were measuring the static pressure at different points inside the bin, and all this instrumentation is for that purpose, and so that we could do the prediction of the distribution of the airflow. And now there are companies like Gatco is a good example, is a marketing and distributing horizontal airflow drying system across Canada. And I have seen similar systems, like I have made presentations in many different countries. And in 2019, I was in China, and they have developed enough horizontal airflow drying systems. So 3 million tons of grain was being dried using horizontal airflow drying system. So other thing I want to point out is, so you understand the static pressure. And also, you need to understand what is the size of the fan you are purchasing. So when you buy a fan, the manufacturer would usually give you a curve, what it refers to as fan characteristics or fan curve. Sometimes they would call that. That's the relationship between the airflow rate fan can provide at different static pressure. And as you can see from this graph, does not matter what type of fan you have, all fans have the same relationship or similar relationship. The slopes are different, but similar relationship, that as the static pressure increases, your amount of airflow coming out of that fan decreases. Why this is very important to understand is that if you were filling the bin, for example, for 1 meter, and then all of a sudden now you fill it for 3 meter, the static pressure by that grain would be 3 times than what was for 1 meter. So if your bin was, your airflow was enough to do the drying for 1 meter depth, then for 3 meter depth, it's not going to work. and it would be under design. So that's why you have to make sure the fan is providing enough air. How we look at that, and then also you need to understand how the air is distributed in different types of configurations. I already showed you the fully perforated, but there are many other air introduction systems. And then using mathematical models, you can look at it how uniformly the air would be distributed, and these are the isopressor lines. Similarly, you can do for hopper bottom bins, and this one also shows how the air would distribute within the bin. Your goal is to have the uniform airflow and sufficient airflow to complete the drying in the required time you allow for it to happen. So that's where the different control strategies come into play. And again, simulations can help you understand what kind of control mechanism you use, and many different possibilities are on this slide. You can have a fan turned on the day you fill the bin and leave it on until certain date, for example, mid-November, and that would be referred to as a continuous on strategy. You can turn on fan in the daytime, you can turn on fan in the nighttime, you can have a timer control that only turn it on for certain time to certain time. So for example, you might turn it on during the daytime and off in the nighttime. You can also do on a thermostat basis, which is based on the temperature, or humidity stats based on humidity, or you can do based on the temperature difference, delta T, delta RH, or natural air drying, or variable heat system. So this is the kind of output you would get then from your simulations when you run the simulations for different. So in this particular example, there are 5 different control mechanisms, which are at the bottom scale you see is the on means continuous, day means only on in the daytime, night means on in the nighttime, NAD is a natural air drying system, so that's using the EMC. And this one, the SAVH, is when we are providing variable heat and using the EMC in it. What you get then on the different colors here are referring to the different harvest date. So August 20th, September 1, September 15, October 1. And what you get, the result is the red line here is the target moisture content. The red solid line horizontal is the target moisture content. You want to dry the grain in this particular example to 14%. And what you get then is there are 3 sections in here. So the one on the left-hand side is for 20% initial moisture content. In the middle is for 18% initial moisture content. And then the right-hand side is 16% initial moisture content. And on the vertical axis, what you see is the moisture content. So these bars are basically showing you the spread. So even though, for example, your moisture may have reached a target moisture, but you still might have a spread between the top to bottom layers of the bin. And as you can see, you have a lot more variability for 20% initial moisture content, and then for the 16% initial moisture content. Other thing I want to point out is that this is for one of the airflow rate. We did similar simulation for many airflow rates. So 2 other graph would be similar, but I'm just explaining this graph. So this is based on 0.5 CFM per bushel or 0.52 meter cube per minute per ton of the grain. And this study was done again by Dr. Singh and myself, and it was published in Canadian Society for Bioengineers Journal. So what our goal is that in terms of the stopping the near ambient air drying or natural air drying is that we want to reach the target moisture content, and the spread on the target moisture content should be as minimal as possible. The blue lines on the top of this graph, like these lines here, basically are the lines which show the success rate of drying, the percent success rate in the year, because this was done on the 30 some years of weather data. So out of that 30 years, how many years the drawing was complete. We are continuing this study. There's a student with me and Dr. Singh currently working, Saran Veera Kumar, who is doing similar simulations now for multiple locations and trying to predict and develop the graphs and guidelines for different grains to show that depending on the kind of weather year you are having, whether your drying would be completed by November 15 or not. And again, his data sets are for Manitoba, Alberta, and Saskatchewan. But similar simulation can be done for Ontario if there was interest and for a particular crop, for example. Okay, so this is for a higher airflow rate, 0.75, and this is for even higher airflow rate, 1 CFM per bushel. So the monitoring of the progress of the cooling or drying is done typically using temperature sensor or relative humidity sensors. And sometimes the manual probing of the bin is done, and you can use the moisture content measurement by oven drying the moisture content or finding out the moisture content by oven drying the sample. And you can use that as a way to know how far the drying has reached. Temperature is a very good indicator, and then you can certainly use the temperature sensors to know where the drying front is and when drying is complete. Okay. So some economic considerations in drying with the for drying and aeration, like typically when you are optimizing your ambient air drying system, the fixed cost, which would be the cost for the bin, the fan system, they are not used for optimization. Typically, they are not part of the optimization process. What you are optimizing is the energy to operate the fan, how many hours fan is running to complete the drying, for example, or energy for supplemental cooling or heating if you are using chilling or heating. Over drying, like as I said, you can market wheat at 14 and a half, and if you dry it to lower moisture content, then there is a loss, shrink loss, or you are basically not selling that moisture, but it gives you a longer storage life. So you have to balance between longer storage life versus marketing at the high moisture. But if you are only storing grain for a very short period, I would say you should try to harvest it as close to as 14% and then try to market as close to as 14%, because if you do below that, then it's a loss. And maximum allowable loss of dry mass is also optimized. So that is when grain is being stored, how much is being converted to because when grain spoils, it produces carbon dioxide, moisture, and heat. And in that biomass, the dry mass is degraded. So typical criteria is used that you should not have more than 0.5 percentage point of the grain dry mass loss to consider the drying successful before spoilage has occurred. So with that, I have already acknowledged my contributors and supporters, and I want to thank you for your time and open for questions.
Okay, perfect. Thank you. That was a lot of information, great information. We do have a couple of questions in the chat, so we'll start with that. One of the questions is they're asking how much will it cost compared to standard system? I know you just talked about the economic benefits from reduced energy, but would you,
So,
and then they were asking vertical versus horizontal as well.
okay, so the system cost, I'm assuming they are talking about the system cost for the whole like full size bin. They already have the bin, and they want to install a perforated floor in that bin and the drying system. Typically, the perforated floor nowadays, and Dr. Singh might have because he has recently bought one, so he might have a much close cost estimate. But my feeling is when the perforated floor probably would be between, depending on the size of the bin, because it would dictate how large the bin is. Perforated floor probably would range between $5,000 to $10,000. Fan probably around $2,000. That does not include the cost of the bin itself. Bins can, again, depending on the size, could be anywhere from $30,000 to $50,000. But I'm assuming the bin is already there. But if you are installing a new bin and purchasing a new bin, I would say I would encourage you to make sure that the perforated system is installed in there. Because it comes in handy for drying of the grain, especially if the grain is in the initial moisture content is 2 to 3 percentage point above the storage moisture content. In terms of the horizontal system, Grain Guard sells them. I think their cost of the horizontal system probably cost-wise are similar to the vertical systems. And so I think because you provide enough perforated area and enough perforated duct to collect the air and to discharge, so the cost is very similar of the two. And also depending on the size of the bin, the number of the size of the somebody would have to then size the duct, center duct, and the collecting duct.
Okay. Just going through. There was another question. It says, was there any resources given to participants? I joined late. There was a document that was put in the chat, but it has disappeared after recording went on. So I'm wondering if we could maybe put it back in the chat.
Yeah, I think the people who joined late, you may not have heard Julie's announcement that these presentations are being recorded and would be made available through YouTube. So you should be able to go back and listen from the beginning. Unless Julie did not start recording at the beginning. I don't know.
So yeah, I noticed it hadn't been put on right away, so we did miss a little bit of your introduction, but maybe we can make up for that later. But yeah, so most of it is being recorded. Okay, so there's another question here. What was the dimension of the bin? Aeration.
Okay, so the dimensions have been most of our our experimental studies has been done in bins ranging from 4 meter to 10 meter diameter. So that's where the experimental studies are. For simulations, it really does not matter because if you have a fully perforated floor, then the size of the bin does not matter because you are basically calculating the amount of airflow per unit per meter cube or per ton of grain. So once you know the amount of grain, you know the size of fan you will need. And if you size the fan properly, which is the airflow going through the grain in meter per second, because it's a meter cube per second divided by the square footage. So it's per meter square of the bin. So in simulations, the size would not matter, but experimental work we have done is anywhere from 4 to 10 meter diameter bins.
Okay, thank you. Next question. Any comments on freezing the bin content with aeration at this time of the year for multi-month storage?
Yeah, I would say freezing usually is not you can certainly freeze the grain or lower the temperature of the grain. Keeping in mind, grain would really not freeze. Like, so for example, wheat would not freeze if the moisture content was below, say, 23%, because there's no enough free moisture in the grain to freeze. So you basically are lowering the moisture content or temperature of the grain. So you certainly can lower the temperature of the grain to whatever, minus 20, or in Winnipeg, you can even lower it to minus 40 if you want. But then you have to be careful in the springtime when you start forcing the warm air. A lot of condensation could occur because of the cold air coming and the surface being cold. A lot of condensation could occur, so you have to be careful to manage that condensation.
Okay. Yeah, so that's all the questions that are in there. Because I'm recording, it seems that I cannot unmute everybody. So you'll just have to keep putting your question in the chat if you have any questions. Gagan, you had a poll that you wanted to put up.
Thanks, Julie. Before I share the poll, Dr. Jas, you said that you studied from the vertical aeration system to the horizontal aeration system, and because the potentially the head, the pressure dropped, so there was less resistance to the motion of air. So more air could be provided for the same energy. Did you happen to study what is the energy um, efficiency that we actually could use? Like
Yeah.
how much energy was saved if we switch from vertical aeration, which is a standard conventional method, to a
Mm.
horizontal system, which is
So
something that you said that you studied and you worked on.
yes, the basically what you are looking at is the because as I showed you that curve, which shows the static pressure increases as the grain depth increases. In the horizontal system, that depth is fixed because you basically are between the radius or from the wall of the perforated tube to the end of the wall. That's fixed, doesn't matter how much grain you fill in it. So what happens is that the static pressure being constant, the airflow rate is then going, and as you remember the fan characteristic, if a static pressure is constant, then the amount of airflow coming out of the fan is also constant. So that's where the efficiency comes. And roughly, I would say on a, because amount of the energy, total energy required, it still would be the same required depending on how much moisture you want to remove from the grain. But what the horizontal air does horizontal air for drying does it gives you more uniform drying, and because your depth or radius is small
Yeah.
compared to the depth of the bin, so it gives you more uniform drying and the less over drying cost. So roughly, I would say the size of the fan you can use in the horizontal drying because of that lower radius is roughly about half of the vertical system.
So, but energy efficiency, in terms of energy efficiency, we don't see any change in the consumption of, whether it is gas or natural, in any source of
Yeah,
energy. So, energy is not affected. It's just that the front moves uniformly in both the directions.
you, and
And
also the size of the fan is reduced, so it would use for the same number of hours energy used would be reduced
okay, so
because your
there would
fan
be a
size
net
is reduced.
effect. Okay,
Yeah,
so for the smaller fan size, we're able to
yeah,
provide more aeration
yeah.
to the bin. Thank you for clarifying that. And in the simulation, I'm sorry, I'm just asking you another question. In the simulation, you just provided one duct with a horizontal to flow it, not multiple ducts were provided at different distances to increase the drying period, right? So it's
Yeah,
just
so
one.
in horizontal, we only had one system, one duct in the middle, and then it's going in the radial direction.
Yeah.
So the what is the design is typically is how many collecting duct you need on the side. So like, do you have a four at the 90-degree angles? If a bin is large, you might need a six or eight, and that's what typically the grain guard would do the calculation and say how many you would need depending on the size of the bin. But the air introduction duct is only one duct.
Yeah, no, that's great. Thank you so much. We do have a couple of more questions, Julie, before I post the poll. Okay, please.
Yeah, so I'm just looking now. So next question here is, do you have any explanation why floor will crust when people overcool their bin? Often see that on corn storage.
When floor would crust,
Yeah, the floor will crust.
yeah, so the way I would think of why that's happening is the moisture is high in the grain, and the high moisture grain probably when you are forcing cold air, the moisture can condense, or that high moisture can then basically clump the kernels together. So there has to be high moisture corn in the bin for crusting to occur. If the corn is dry, there is no reason for it to crust. As I said, like for wheat, we did studies, and wheat would not freeze or crust until about 23% moisture content. So if your wheat was 16, 17, 18% moisture content, which is even above the dry moisture, would not crust.
Okay.
So there has
He
to be a
added
high
a,
moisture.
oh,
There
sorry,
has
he
to be
added,
high moisture for crusting to occur.
oh, okay. He put in a comment in here, it was dry corn.
Well, then I have to look, honestly, I have to look at the what they were doing, and because dry corn should not crust.
Okay. Just a comment here. I was intrigued by farming in the north of Canada, so I saw this webinar and decided to join. I was thinking of attempting to grow wheat, so I thought this was a good way to preserve grain.
Yeah, certainly we have done studies which shows that Churchill is the best place to store grain, for example, because of the weather conditions in that area. And you can lower the temperature in a significant way, and which eliminates some of the mold problems, the insect problems. So certainly northern part of Canada would be a better place to store grain and would have less problems with the storage as long as grain is dried and not leave it at high moisture.
Okay. So in the chat, Matthew left his email address and he would like to discuss later. So we'll provide you with that email address and maybe you can follow up with him after.
Yeah, or my email address is on the slide, and he can maybe send me an email.
Okay, yeah, we can do that.
Yeah.
Okay, Matthew, if you want to send Dr. Javas an email. Okay, so I do have another question here. Could crusting in dry corn be caused sorry, things are moving around on me. Sorry. Okay. Could the crusting in dry corn be cause of high moisture in the fines with the grain?
Yeah, that's possible. So there has to be high moisture somewhere. So whether it's in the fines in the grain, but the grain mass has to have a high moisture for crusting to occur. Because crusting is caused by two things. Either it could be the low temperature freezing, if there's a high moisture, or high moisture would cause molding, and the molding can create again high moisture, which then brings the kernels together and they stick, and then the crusting would occur.
Okay. So the comment here says, I have seen this as well with high amount of fines in wheat that was bind at 15% moisture and high amounts of fines.
Yeah, and 15% moisture is a high moisture if you want to do long-term storage. So that in itself would have caused the problem, plus fines on top of that.
Okay.
Yeah,
Okay,
thank you. Yeah, thank you, Dr. JS.
So
I
I
think
can
you,
stop share now.
yeah, thank you for an insightful session. And I'm going to share a poll by the time Dr. Singh takes the seat. So I am just asking if you have a on-farm grain dryer, what type is it, and what is the primary source of energy for heat generation that you use for drying? So um, uh, we will appreciate your answers. It just gives us an idea what type of on-farm grain dryers are being used presently by the producers or the farmers in Ontario or in Alberta. Yeah, I would invite Dr. Singh now. He can, this poll is going to be there for a minute or so, and then Dr. Singh can share his slides. Okay, I think we can go ahead, Julie. I will just stop or end the poll.
Okay, so we'll just, I'm just going to continue to monitor the chat. So continue to put your questions in the chat. And we will have another Q&A session after Dr. Singh's presentation.
Be able to see my slides?
We can, but we're not seeing the presenter's view right now.
Okay. How about it now?
Yes, now we can see the presenter's view. Thank you.
Should I start?
Yes, please.
Good evening, everyone, and thanks for joining this webinar. I would like to thank Dr. Madan Patra for the opportunity for me to share my experience on from grain drying. We have already learned a lot about grain drying fundamentals from Dr. Jaz, and I was very fortunate to be trained directly under him. So you will again see some of the information repeated, but I will focus more mainly on the high temperature drying. Before I start, I want to give little bit background about my program. My name is Chandra Singh. I am RDAR Research Chair in Agriculture Engineering and Technology at Lethbridge Polytechnic. RDAR is a provincial funder in Alberta that funds applied research in agri-food. Our center focuses on storage, handling, and processing of major Alberta crops, which are also common in other provinces, such as cereals, oilseeds, pulses, potatoes, and sugar beets. Our program has received funding of over $10 million in past 5 years. That includes 2.4 million CFI grant for establishing the center. That includes the grain storage and handling research facility, which has a 12 million BTU grain dryer, high temperature grain dryer, 320,000 bushel grain bins equipped with fully monitoring and automated fan and heater control. My teams usually have 5 to 8 postdoctoral fellows with background in biosystems, food engineering, food chemistry, food science, and horticulture. So I will be talking mainly about high temperature dryers, dryer performance, and some of the work that we've done extensively in Alberta for wheat drying, and our recent experiment for the corn drying at our own research farm, and what lessons we learned from commissioning of the dryer, and then I will summarize my presentation. So why high temperature drying? There's several reasons that the farmers, they choose high temperature drying. And number one is, as we live in very cold and extreme weather conditions, minimal weather dependency. So it is less dependent on the weather, whereas a cold, wet, snowy conditions limit in-bin drying. Drying is continuous, so it's faster also, which can prevent spoilers. As we saw that the safest storage time is moisture and temperature combination and time. It can remove up to 10% moisture in single pass, whereas in bin systems, typically 3 to 4% is ideal that you can eliminate. Wide variety of grains can be dried in high temperature drying, and these dryers are fully automated and remotely monitored. There are three main types of high temperature dryers. You might have already come across these names. These are relative to relative flow of grain and air, their movement. They're called cross flow dryer, mixed flow dryer, and double flow dryer. So I'll tell a little bit more about it. As name suggests, cross flow dryer, the grain and airflow moment is perpendicular. In this slide, if you look on your right side, the grain from the holding bin is moving down, whereas the heated air from the plenum is moving horizontally and out of the dryer and captures the moisture. This is simpler in design. So a lot of farmers have these dryers and they work fine, but they may not be very energy efficient. So there is another type of drying systems, and many claim to be better. In this, as name suggests, the grain and air are mixed through that when the grain is moving through the dryer column. So one advantage is that there is a more time for the grain to be on the dryer in contact with hot air. If you look on to your right side, the triangles, red and blue. So these are the ducts. Red ducts or the triangles, if you see, they are connected to the plenum uh, for the heated air to move inside the dryer, but they are close to outside environment, where that air moves and mixes with the grain and captures the moisture. And then as you see the blue triangles, and they are close to the plenum, to the hot air, but they take the moisture after the grain, the air moves through the grain and take it out. So that's why the name suggests wind. And they have large capacity, as you can see here. The place on the left side, this is the form that we included in our study. A third type dryer that's not very common yet based on our study, but this is very interesting. This utilizes the heat from cooling section through recirculation. So if you look on to your right side, there's hot air coming from the top, and then the dryer bed is moving the grain, which can adjust the height, means how much amount of grain is moving through the. But in the cooling section at the bottom, where the blue line area, if you see, that fresh air moves through the hot grain and cools the grain down, and then that heated grain is again recirculated. That's why it's a recirculatory system, and it has its own advantages. How do measure dryer performance? There are several variables that you can say that, yeah, these are the important, and I would say all are important. Number one is energy. How much fuel consumption is, how much electricity is required for the fan, auger, and other moving equipment. And fuel is mainly natural gas or propane. We focus on the natural gas, which is very common for these dryers in Alberta. Dryer capacity is also very important, whether that dryer is sufficient for your needs. Are you able to move enough grain dry every day? So it is very important. And that's, if you're not able to meet your requirement with that capacity, maybe this energy efficient but not fit for you. So that should be a consideration. Moisture removed. How much moisture is actually removed from the dryer per hour basis? So this is another important factor. Are you able to, and again, if you try to remove more moisture, that means the capacity will be lower. Quality of the dried grain. Because the grain is exposed to the high heat compared to in-bin drying system, even with the low temperature heaters, where heat is mild. So as the grain temperature affected by high plenum air temperature is affecting the quality. That's another important parameter for many crops. For example, wheat. Overall, efficiency is a term that used for the dryer performance, dryer efficiency. It's broadly used and it covers broad performance, and it is specific energy. So how much theoretical energy is required actually fundamentally to dry, but that's not the case. The actual amount of the fuel required or burned and electricity consumption is way more than. So that is the term used to define how efficient the drying system is. This is a formula. I'm not going into detail, but this is used. So it uses the theoretical energy calculation on the top, and then it calculates the fuel by metering the natural gas or propane and electricity, and that ratio tells how efficient is the drying system. In our study, this was funded by Alberta Wheat Commissions. Now it's called Alberta Grains, Saskatchewan Wheat Development Commission, ARDAR, CAF funding, as well as Alberta Innovate. So we partner with the farms across the Alberta. The bottom side is south, where I am located near Lethbridge, and the top is almost in the Peace and North region. Interestingly, we tried to look for three main types: in-bin natural air drying, in-bin natural air drying with low temperature heaters, high temperature drying, and combination drying, which is the natural air drying, high temperature drying, and a combination of natural air drying. We found most of the high temperature drying happening on the north side, further north of Edmonton. And most of the high temperature drying farms or in that area. So these are different type of dryers that I mentioned. We were fortunate to get mixed flow dryer, glass flow dryer, as well as one recirculatory dryer, which is called, they call it as a double flow dryer. And they are very new. Some of them are very old, relatively smaller capacity of say 25, 30 tons per hour to all the way up to 118 or 120 tons per hour capacity. And different mix of designs, number of fans in the fan location, as well as the different uh, type, type of the mechanism of different fans where they are located within those dryers. We did this study for 3 years. We collected the data in some forms up to about 1 to 2 weeks in about 100,000 bushels of dried grain from some of the dryers by my team. What data did we collect and why we collect? I showed you that we need to measure the performance. So we use to measure initial moisture content when grain enters the dryer and final moisture content when it leaves the dryer. Grain temperature before the drying as well as after drying. Fuel consumption, natural gas was the main fuel for the burner. So we took the reading of the meter before we started a particular batch, and then it typically 30 minutes. And then after every 30 minutes, we took another reading, and they were all normalized data from these readings. Similarly, we have amps consumed for the fans in August specified for that period. And then we calculated a specific energy, the per ton of moisture removed, and then same with different dryers. And we came to this, some of the conclusions here. So the first one is very simple, but it still is very important. That smaller the dryer and ambient temperature difference. So the top graph you see, the bottom is the difference, dryer minus ambient. So if ambient, that difference is less, mean that the air is already heated enough. It doesn't require a lot more heating. And obviously then we found that efficiency is higher. Second, we also found the grain temperature. When the grain with lower temperature, as you can see in the bottom chart here, a graph, that if the grain temperature is low, for example, 15 and below, then we have, that was the lowest, but our efficiency is close to 40 or below 40%. As the grain temperature increases, our efficiency goes up. But after a certain point, then it started to come down because that gradient is less now between grain and the plenum temperature. So these are the two variables that suggest that if you're running the dryer very early in the morning in the winter, that will be the lowest efficiency. And if the grain is cooler, then also the cost of drying will be more. So that's why in some studies, it's suggested that if you can keep the grain into bin where or the preheat it, and that preheating actually helps to improve the drying efficiency. So why if you're leaving it on a holding bin, probably it will respire, increase the temperature. That sometimes help. Or if you can use a low temperature heater and heat that in bin in holding bin and then move into the dryer. This is the effect of the grain moisture on the efficiency. So this is the difference between initial and final moisture. What that means, how many percentage of moisture you are removing. What it tells that if you are using this high temperature dryer for 2% or less moisture or 3%, they are not efficient. And I don't think that anybody should use high temperature dryer if they have to eliminate 2 to 3%. In-bin drying system, Dr. Jazz talked a lot about and gave so much information. They are sufficient to do the job. Whereas if you need a higher amount of moisture removal, 4 to 5%, and at least 3% or more, then these systems are more energy efficient, as this chart shows here. Also, in this case, the orange, the boxes that shows the top efficiency, the double flow dryer, which uses the recirculatory heat system, has the highest efficiency of over 91% compared to all other dryers. Also, we looked at the cost of drying with increasing initial grain moisture. So if you look at the bar chart here, what it tells you is that if you are, as again, it's not obviously in the previous slide, I showed you that efficiency is less for removing less than 3% moisture, 2%. And that is impacting the drying cost. So it is obvious. So if you look at just this chart on your right side, the very top, A, just one, there are different dryers, but just one, the plot A. If you are removing one is, so 16 to 17% is the initial moisture, the blue dot solid in the first side. If that means if you have already bringing in the grain wheat 16 to 17% and targeting 14%, then you are removing basically 1 to 2% moisture. What it does, its cost of per ton drying is very high. Whereas if you, again, if your initial moisture is more, so 20, 21%, then your cost per ton of moisture removal is less. So again, it's again suggestion that if you have lower moisture already grain, tough grain, 16 to 17% in this case wheat, and if you have to remove less than 3% moisture, these systems will cost you more. We also did the cost prediction and estimate for each dryer time. So these are different dryers. The blue solid bar is the fuel cost, but also the farmers have to pay carbon levy on the fuel. And that's in each of the chart, the top one you can see, the carbon levy cost is more than the fuel cost. The highest cost for large capacity dryer in one of the less efficient 8 under fan mixed flow dryer was average about 113.4 to 116.3 ton per ton of the moisture removed. So just one thing here I want to clarify. It's not per ton of dried grain. I was asked this question in one of the presentations. I want to clarify that amount of the dollar figure is for tons of moisture removed, but still it's high compared to other more efficient dryers. As the dryer efficiency showed, the least cost observed with the double flow dryer, which was average about 63.5 to $91 per ton of moisture removed. Interestingly, carbon levies were 25% higher than the fuel costs. So if the fuel cost was $1, it will cost the farmer to dry the grain $2.25 because there $1.25 carbon levy on the fuel. As the carbon levy is progressive, every year it's going to go up until 2023. We estimated that if we have the same pattern and same fuel consumption, what the cost of the drying will look like. And these projections show here that up to by 2030, the drying costs due to the carbon levies will be 92 to 168% higher. What it's currently, if you have the same dryer, same operations, no change. So it's going to have a huge impact on your drying costs. So it's better how you can improve dryer efficiency or drying operation efficiency and how you can reduce that cost. We also did a combination drying. So as the name suggests, that high temperature drying followed by then in-bin drying. So basically, you dry the grain 1 to 2% higher than your target or you are hoping to store at. And then remove that additional 1 to 2% moisture using in-bin system. In this case, a 6-point total reduction. Out of that, 1.5% moisture removal happened in grain bin. One important thing we just learned that is the airflow. In this bin has a very good airflow from 0.4 to 0.8 CFM per bushel in that range based on how much grain you have. And this in-bin drying was fully automated, which took about 8 to 13 days. And we compared conventional high temperature drying and using combination drying with all the parameters same. And we estimated that you save from 19 to 33% more energy by using combination drying rather than having all the drying done in high temperature drying system. So if you look at the cost of the drying per ton, this is significant saving without not having to improve much in terms of your infrastructure. Now I come to our corn drying experience in Alberta. So this is part of our Advanced Post-Harvest Technology Center's grain storage and handling research facility. As you can see here, we have a mixed flow 8 years double burner natural gas dryer with 12 million BTU per hour capacity. It has individual temperature settings for each burner, each of 2 burners. It has option for dry, including full heat, heat and cool. That means that we can use both the fans to either run at the full heat, or we can use one burner, the top typically to dry, and the bottom we can use it to cool, to remove some moisture due to evaporative cooling. This is fully automated facility. And we also have remote monitoring option where we can remotely monitor moisture and temperature and overall drying operation. We did a study earlier on in-bin drying of wheat, which I'm not presenting, but we use our drying system, in-bin aeration system, with low temperature heaters and dried durum wheat from 18 to about 14% using these bins. These bins have, one of the bin is with the natural gas heater, low temperature heaters, and others are with propane. So we have fuel options. Actually, 3 bins we can run, one with the ambient air, no fuel, if we decide. The second one we can run with the propane as a fuel. And third one we can run as natural gas, as well as we can compare with the cost of high temperature drying by drying in high temperature dryer only. So this is our partnering farm this year. We usually work with the farmers. We get grain from them and we dry store at no cost. And that's how we conduct the research and collect the data from these bins and the dryer. This is a AGI NECO drying system, and this is the control system. It might vary based the user interface may vary based on what type of dryer you have, but most of the advanced dryer, they have similar PLC-based control system. So if you look on your left side, you can select the card, and then we have 2 fans, number fan 1, number 2. Number 1, when we started commissioning this year, was giving some high temperature. So we reduced the speed to 90%. They are VFDs, so not running at full speed. And we are still trying to figure it out why it's not operating at 100% without producing any heat from the motor. The second dryer we ran actually at 100% power. It's recommended that even full heat mode, the bottom should be less than the top burner. So we operated it at about 200, the top burner Fahrenheit, and 180 at the lower or the bottom burner. Because the more the heat is removed from, the more moisture removed from the top column, and then the bottom one requires less heating of the grain. Also, You can input your grain moisture. You can collect the samples from the sample collector from the dryer, and also the discharge rate, which is also very important. That how much moisture. If you're removing less moisture, then your discharge rate can go higher. That means you're removing more grain per hour from the dryer. But if you are removing excess moisture, then the grain needs to be for longer time in the dryer. And these are the things that once you start drying, you see the operations and then play around it, and then you'll figure it out. One thing here is the target moisture, that's 16. That's what we had because we wanted to bring it to 14, 14.5 in the bin. The other thing is the outlet dry grain that you have to enter into it. So the system is still calibrating, running according to the output moisture and input moisture. So it's very important that you take the samples regularly, measure in your benchtop moisture meter, feed that so system knows what is inlet moisture and what is the outlet moisture, and then it will make some adjustment. It will have some learning based on this, but it's very, very critical. If these inputs are wrong, the dryer will not make best decision if it's running on automated mode, which we were trying to do here. So corn is a new crop, relatively new crop in Alberta. There might be some random farmers growing it, but it's getting some more attention, and acreage is growing every year. So they thought they are combining the grain. When they got here, it was 35% moisture content, and they plan to dry it down to 14%. Well, that dryer is 12 million BTU. It has a lot of heat, but it's not capable to remove almost 20% from it. So what we did was that we dried it to 25% around that in one pass and moved it to in the bin. We have a pneumatic conveying system with the blower that automatically moves the grain to in the bin. So we dried from 35% to 25%, moved that grain into the grain bin, storage bin next to it, and then unload it and put that back again into the holding bin. And from 25, then we dried it to 15%. So this is what we were able to do here at our own research farm. First time learning, everything doing first time. We had several issues, which I'll talk in the next slide. But what I'm showing is that why the temperature and moisture cable is very important. Most of the grain that came about was 15% here, that range, or 16. But we were running the fan, so it might have removed some moisture. But as you can see here, that most of the grain is sitting at about 14 to 14.5%. And that was November 4th. And then they moved the grain from the bin. They sold to the feedlot right away. If they had taken it, so the feedlots would not take any grain above 17%, again 35%. And if it is even 17% and more than the maximum moisture they take without discount is 15. So they would have been discounted for 2%. So excess moisture. But with the drying, they were able to deliver that grain within 15% moisture, no discount, no issue. So this is the advantage of having the drying capacity. We installed the dryer about 2 years ago here at our farm, research farm. Last year, we tried to get some tough grain. Tough means over 17% wheat. We did not get. Southern Alberta is usually dry. It's very dry, so we get dry grain combined. But corn takes longer, and its harvesting is delayed, and that's why we are fortunate to find a farmer who was willing to work with us and provide the grain for the drying. First thing was that we found that there are two moisture sensors. One is where the grain inlet is at the top, and one is where the grain is leaving the dryer and near the sample holder. Somehow they were swapped. So our inlet moisture was coming at 16 and outgoing moisture was going at 25, 35. That gave crazy run for a few hours before we figure that out. So it's very important that sensors are calibrated. They are marked, they are located in right spot to make sure that your inputs to the dryer is correct for automate. Regular sampling is also important so that you can also feed what the value actually you're getting, not just relying on the sensors, but actually what you are inputting to the dryer and what you are taking out of the dryer. And that's how these systems learn smartly and operate in much more efficient way. We also noticed that clogging of discharge sample holder. So what happened where you're supposed to take the samples when the grain is leaving the dryer, it clogged. So whatever grain it has, it was giving you moisture for that grain, but maybe that would have been 3 hours ago. So that may be 15, but now different conditions, you are moving the grain, which is 17%, for example, into the bin, thinking that's 15%. So sampling is again very important and make sure that the discharge holder is not clogged. We also ran into the issue with the pencil auger and load auger. Pencil auger is the one that's taking the grain from the holding bin and then putting into the load auger, and that load auger moves to the top. They were not keeping up with the capacity. So dryer will be unloaded, not loaded, unloaded faster, but loading will be slowed out, and that will shut off everything. So when you are planning a new drying system, high temperature drying, these things from your capacity of your holding bin to your capacity of your pencil auger to load auger and your dryer capacity, and from dryer to bin, it's all should be planned. And if one thing breaks, even a small thing, it's going to break down everything. And if you are running those dryers in the peak of the season, you don't have any time to spare for these things. So these should be planned when you are installing, commissioning, planning a new drying system for your farm. As I mentioned, we had the issue with the motor heating and we don't know. So the top fan blower motor would heat and then it will shut it off. So we reduced the operation to 90% and then it ran for the season, but these are the issues that you might see and we have to figure that out. Though it was a new system, but we saw that the burner needed proper cleaning. Luckily, we had the guy from AGI for commissioning. He cleaned. But that's another thing recommended, that make sure your burner is properly cleaned every season before you start operating the dryer. Not only the burner, but your whole drying system, everything should be properly cleaned. We found one interesting thing. There's a small tube that measures the back pressure from the fan to make sure the fan is running, it's delivering the pressure, and that's used as a closed loop system. There was a bee or insect inside, and that very tiny insect was clogging that tube. So we were not getting any pressure. The fan was running, but the system was not getting any pressure. And it will run for 5 minutes. As soon as it did not get a feedback pressure, it will shut it off. So these are the smaller things that might happen to your operations as well. So everything should be clean, checked, inspected before you start your drying operation for the season. Setting right discharge rate, we played around with it. Burner temperature and target moisture. All these are very important. And as you operate, you know the capacity of dryer, you know what it can do, what magic it has. Eventually, you will figure these out. This is my summary. I would like to conclude with double flow dryer with heat recirculation was most energy efficient in our wheat drying study. Discharge rate should be optimized. This is very critical for your target moisture and energy efficiency. Grain with initial moisture below 17%. In this case, it's a wheat, should not be used in high temperature dryer because it won't be energy efficient unless you have no other options. Grain temperature below 15 degrees Celsius also reduces your energy efficiency. Regular grain sampling for moisture calibration is very critical. So make sure that your benchtop moisture meter is calibrated, it's accurate, and you are feeding that to your system for regular operations. We also explored combination drying, which can remove 1 to 2% additional moisture in a storage bin and resulting up to 33% energy saving. We use some of the dryers full heat and some use heat and cool, but our recommendation will be use full heat mode, and the cooling part can be done in bin and the combination drying. And two advantages, more energy efficient. It will also increase your dryer efficiency. Normally, typically in any dryer with heat cool mode, if you are using full heat, you can move more grain per ton, more volume of grain per hour in terms of the bushels per hour. With this, I would like to thank my collaborators. It's not just the green, but for my advanced post-harvest technology program and for funders who have supported my advanced post-harvest technology research center at Lethbridge Polytechnic, as well as my team, including students, postdocs, research associates, and technicians. Thank you.
Thank you, Dr. Sain. Again, lots of information, certainly lots of food for thought in all of that. So I'm looking at the chat, and there was a question that came in just before Dr. Sain started his presentation. So I'm assuming it might be a question for Dr. Jazz, but I guess I'll throw it to both of you, if it's okay. So the question is, how much efficiency improvement can be expected by automating dryer operation based on internal and external condition, and which factor should be prioritized to maximize performance?
Yeah, so I can certainly add, like, I think the one of the figures I showed you for different harvest dates and different control strategy. One of the strategy was basically to use the variable heat. Another one was based on the EMC or equilibrium moisture content. And as you can see, if you remember that graph, basically you had a less spread when you were using variable heating because it was able to optimize the amount of heat required to dry the grain in the required time. So to me, I think you would have a better drying if you have a control of on the airflow, control on the temperature, and then have a good knowledge of the initial moisture content and harvest date if you are using in-bin drying. Dr. Singh can respond to from the perspective of high temperature dry.
So I don't have your data on comparing with non-automated, but most of the dryers that we work, they have at least partial automation done in drying system. Our drying system is fully automated, but we don't have your data this year yet. From the grain bin side, we in our bin that we did with the wheat study, we saw about 25 to 40% energy efficiency if you run without any automation. So it's not just the energy efficiency part, but also you have less spread. So you don't have any shrink. So for example, if you're selling the grain at 14%, which is accepted by the elevator, and if you dry it down to 11 or 12%, then you are losing 2 to 3% of value of the crop just because you are over dried and there is no premium for it. Whereas if you automate it, your shrink might be within 1%. So even 2% of saving on your weight in, say, 20,000 bushel, 30,000 bushel, and 2% of the value is just the amount that you can save by automating the system in addition to energy savings.
Okay. Next question. How accurate are dryer moisture sensors compared to calibrated moisture testers?
They are pretty accurate and very expensive too. I can tell our two drying system, and I've not cross-checked yet, but they are about $8,000. So if you pay $4,000 for a sensor, I expect it to be accurate. The benchtop meters, there is a trick. If you take the grain right away from the dryer sample holder and measure it right away, you will not get accurate results. So make sure you bring that sample, let it sit for a while, let it bring it stabilize to room temperature, and then also have the right type of moisture meter. I've seen the old 919 moisture meter, Labotronics, that any farmer would be familiar here with. They tend to give you high moisture than actual. Whereas the newer moisture meters that recommended by Grain Commission, they are more accurate. And they are quick, so you don't have to look into the table. And it gives you the correct reading right away. So this is important that you bring the samples, let it stabilize. If you put the hot grain into the dryer, then it will not be appropriate calibration inside the system, so it will give you inaccurate readings.
Okay. Next question. Grain moisture tests should be performed on clean grain according to CJC. How do you compensate for wet weed seeds in the bin if you are sieving them out to perform a moisture test?
Yeah, well, clean grain will give you the moisture of clean grain. But if you have more foreign material, broken anything, then you want to know the overall moisture because that's what you are letting into your dryer. So that's accurate. But if you have a clean grain moisture with the moisture tester, it will not be the same as if you have a grain with more fines, brokens, or foreign material. So I would rather use the actual sample that you are drying or storing. And it may not be very accurate because your calibration might have been built with clean grain, and I assume so. So you might see some differences, but I would rely on what actual your accurate moisture that you have in your bin. And that's how you can monitor and see what conditions are favorable for storage.
Okay. How much saving is there using natural gas over propane?
A big difference. I don't have numbers, but the huge difference in the cost wise, and that's why none of the drying system in northern Alberta have actually propane. And also it depends. Some farmers they don't have that option of natural gas. So, for example, for our farm, it was less than a kilometer, maybe 500 meter that we have to bring in the pipeline, and it costed us about $70,000. So if somebody is few miles away from a natural gas line, this is not an option. So they have no choice but to have propane as energy source. But wherever there is an option, by default, anybody will go with the natural gas.
Okay. Next question. Have you found if there's a particular advantage of running at a high plenum temperature versus a low plenum temperature?
Yes, your high temperature means your drying is faster. So that's advantage. but I will say disadvantage. In our wheat drying study, we only not, though I talk about the drying, we also looked at the milling quality as well as the baking quality that we are still producing the results, not producing results, but working on publications. So if you have over 180 degree Fahrenheit, I'm talking about the wheat, then it affects some of the milling and baking parameters down the line. As a farmer, you may not be affected directly because that's not a grade, or it may not be in our contract. But if the millers, they are receiving that grain, if you're supplying locally, and if they see the issue, then it might come back. So that's a disadvantage. With the corn, yes, you can run into high temperature at high elevated temperature. It has more tolerance. But if you go too high, then also start to develop the cracks. So you will see the cracks developing into the seed. So ideally, it's most of the dryer, if you look into the manual, they have given for each grain what should be you can play a little bit with those numbers, but I would follow whatever the recommendation for that crop and for that particular dryer manufacturer is.
Okay. Next question. We're using the Perton AM 5200. We sell those moisture testers, precision calibration and equipment.
Yes, I believe that's the one shown in the picture. Yeah.
Okay. Okay.
Yeah, so that's approved by Grain Commission in Canada, and that's also a standard moisture meter in US. So if you're using that moisture meter and you plan to sell your grain in US, you will not see moisture difference. That will use say 16 here, 15, and then you go there, you may find 17. But if you are using 919 meter, and then you might see those differences between this UGMA-based moisture meter pattern and 919 meter. Usually, I have observed that 919 is maybe 1 to 2% higher. So if you are measuring with 919, you think it's high and might be safer side when you deliver, and that reading will go down.
Okay. Next question. We know that moisture sensors on combines are affected by test weight, and combine
Yes.
moisture sensors technology come with a dryer control system. So how does dryer control nowadays deal with test weight?
So test weight is of the dried grain is different than the test weight of your tough grain, right? But the tough grain moisture reading in the combined should be calibrated with using that test weight in that moisture range. I would not say that they were accurate, but they should be within acceptable range. Whereas your anything with the dried grain, you will be safer within 0.5 to 1%, where the combine might give you, and I have not validated and compared that data, but because your grain moisture range is high, so you might be combining 20%, and your test bed will be different. So you might see if its calibration is different, you might see higher error in combine, which is typically the case, I would say. But as you dry it down, that's what is more important when you sell, to make sure that your moisture reading are correct and you are not discounted, where you take, say, you thinking 14% wheat and elevator thinks it's 15, you will be discounted. Was that question, if I clarified?
I'll see if he comments on it. There is a follow-up question to the question where they were asking about how to compensate for wet weed seeds in your bin. And so the follow-up question is, so how grain moisture cable deals with that foreign material?
Yes, so that's why the grain moisture cable, and those who have those cables, and I have been working with these cables a long time now. Within your cable, you might be within 0.5% 1 year with the cleaner grain. Next year, if you have more foreign material, more broken in the crop, or not very high quality test weight crop, and then you might see that that's off by a percentage or more than that. So that's the challenge, but there's no other option, reasonable, cheaper option than the moisture cables in the grain bin. So still, you know a trend, you are close enough to see that nothing is going to happen to the grain. But that's the challenge with the cables here. They are not as consistent as your moisture meters.
Okay. So going back to fuel. So someone is asking, has anyone used biomass as a at its heat source instead of fossil fuel?
So can you please repeat the question?
Sorry. Yes. Has anyone used biomass as a heat source instead of fossil fuel? So instead of propane or natural gas. So
Honestly, that's not an option in Alberta when you are trying to dry it to below zero temperature or within 2 to 3 weeks. And it's a huge volume of the grain that we are dealing with. I worked many years ago with the biomass when I was doing my master's back in India, and I was working with a rice mill, and they use rice husks to produce a steam, and that steam will be used in direct heating of a batch tower dryer to dry parboiled rice. But here, it's such a huge volume of the grain that we are dealing with in such short time, and it's extreme weather. I think it's not an option here for any average farmer in Alberta.
not in Alberta. Okay, someone put a comment in the chat box with a link saying there is a company in Manitoba that does that. SCW, so people could go and check that out. Next question. It says 919 are generally higher on wet grain. I'm not sure what that must be some other sensor. 919 are generally higher on wet grain, but lower on dry grain. The Perton is 150 versus 18 MHZ of the 919. So the pattern sees more moisture because it looks deeper into the kernel, especially on large grain like corn.
Yes, so there are two different technologies, different frequencies that they use, and that's why it's licensed in US, this technique and newer technology, and Canada followed it after the US. So there are two companies. Now there may be more, but when they started in 2013, the Dickinson and Burton, they had the license to produce these meters, and they were within 0.5 to 1% moisture range compared to the oven dry. If you look at NIR analyzers, they are definitely within 0.5%. But the cost, they are probably about $5,000, these moisture meters. Those you're looking at about 35,000, 35 for each, the basic ones. So 919 is, I think I got one for 2,500 couple of years. So from $2,500 or $2,000, then you're going to $5,000 to $6,000, and then going 35,000 to 70, 80,000 if you are combining those NIR analyzer with protein, oil, and everything. So it's cost. So what's your need? How sensitive you are to the moisture? If somebody is a popcorn producer, they want to pop it all within 13 to 13.5%. Yes, definitely $35,000 is worth. But if you're selling your corn to a feedlot, maybe not.
Okay. So there's a last question here in the chat. It's regarding, again, the weight. So when test weight change, the dryer moisture sensor, oops, just jumped on me. When test weight change, the dryer moisture sensor gets off. So does company have to figure out with this?
Yeah, usually they have a, so it's not actually measured, they are measuring in a range. As long as you are range, it will extrapolate or interpolate whatever the mechanism it uses. And I'm not familiar with the exact type of dryer, but if it's really, really off, maybe that's not a typical crop that you produce, or maybe something wrong with the sensors. So definitely calling out the manufacturer or the supplier or those sensors will be the best thing to do. But it could happen. Also, the
Okay.
test weight, sorry, just want to comment that the test weight, how they are measured in Canada and US are different. So I think the one is called every system, the test weight. And if you can go to the Canadian Grain Commission's website and Winchester, so they use a different bushels that he use. One is the grain is compacted and one is not compacted. So if you have a contract with a company in US and you are delivering the corn or other grain to US, you better use what test weight they use, not your test weight. And you same thing, your machine might be calibrated for Canada for test weight, and it may not be same if you're delivering it to the US elevator. So there's slight difference, but if it is in your contract, that it might affect you really. So it's important to understand those two test weights. One is the volume is different in the bushels. US bushel is different that empirical bushel that's used here in Canada. Plus also how you fill the container, whether it's compacted or it's not compact, that will also impact the amount of grain. So these two make both those Avery and Winchester, I think, systems different.
Okay. Thank you. And there's a comment in the chat. Every equals compaction factor. This is what we use in Canada with
Yes.
Winchester equals
Yes.
US.
Yeah.
So moisture calibration also differ between different countries.
Yes.
So good to know. Okay, so that I will pass it over to Gagan to do the closing remark and put up the poll.
Thank you so much, Dr. Singh. It was really informative. I'm sharing the poll with the audience, with the attendees, to please put on if you would like some future topics for the seminar, and if the information was helpful. I know that there was a lot of information that was provided from the academic background to the extension. So it started with academia and went to the extension, little things like cleaning the fans, selection of the fans, and how you can recirculate the air to increase the efficiency, reduce the energy. All these are very important factors. Crusting of corn is a major concern. I know the conditions in Alberta are different from that of Ontario. Ontario produces a lot of corn because they have a rotation of wheat, corn, and soy, whereas Alberta is still picking up. And we were trying to cater the whole of Ontario through this seminar because we had a lot of requests from North as well. So it was a good starting point, I would say, and learning curve for us as well, that what are the needs of our stakeholders, the producers, the researchers, the academia people, and extension specialists, and especially the government, how we can assist them with the new things. I learned a lot because the conventional system is using the regular selenium on the floor, and the vertical motion is still going on for the aeration. Horizontal are not still very common in Ontario. And And we don't do a lot of wheat drying in Ontario because when it is harvested, the temperatures are high. And though it is recommended, as you said, some of the processors actually wish to have certain quality, parameters for the baking products. So they actually are trying to encourage people to dry wheat and then sell it to the elevators. So that was really, really insightful, and I hope everybody enjoyed it. So I am launching the poll for everybody to participate and contribute towards it. A big thank you to our speakers. Dr. JS had to leave because he had another meeting, and so he said thank you to everyone for attending, and he has shared his email address. In case if you have any further questions, my email address is there. Dr. JS has shared his, Dr. Singh has shared his, and they were kind enough to, say that you can connect with them directly. Um, we know that for everyone, farmers, producers, researchers, we know it is vital. Grain drying is very vital, and storage are for maintaining the quality and ensuring the strong returns to the farmers. At the same time, it's just a message. Let's remember to be mindful of our neighbors while operating the grain dryers to minimize the noise and minimize the nuisance. So if anybody is thinking or planning of, installing a grain dryer, please be mindful. Make the maximum distance, keep the maximum distance to avoid any kinds of nuisance complaints. So I would say with this note, it was a wonderful section. Thank you so very much. We are really obliged that you agreed. I know it took a long time, at least 2 to 3 months of planning, but finally, I'm happy that we were able to deliver the way we had anticipated without any technical issues. A big thank you to OMAFA for letting us host this and the attendees who participated in it. To my colleagues, Julie and Ben Rosser, they just supported the whole process of planning and execution. And it's been wonderful interactive webinar, and I hope we all leave with new knowledge and ideas. Again, a big thank you. And this recording will be available on YouTube channel as shared by Julie on it. And we will share the link with you. We have your emails and definitely a feedback survey also, which you will get in your emails, and we'll be obliged if you can return back to us. And wishing you and your families a very warm, joyful holiday season. Take care and good night.